Okay, so in chemistry, we just finished up balancing equations and reactions and making sure that we had the right number of atoms of each type on either side of the equation and the reactants and the products. What we're going to do now is we're going to move away from balancing equations and we're going to move into classifying the different types of reactions or equations that we can see in our chemistry class. So chemical reactions come in many different forms. In our class, we're going to focus on just a 5-ish major types. So just as a little rehash of what is a chemical reaction is where we produce a new substance. Now, a lot of students like to think that if a chemical reaction works where I take something like oxygen gas and I directly change that atom into a new substance, something like solid gold. Now, if you're able to figure that out, please let me know, as that would really help me retire a bit earlier here. This is not how chemistry works. Chemistry works by taking elements and rearranging them. So we don't destroy or create any new atoms. What we're simply doing is we're taking what's already there, kind of like Legos, or if you play Minecraft, you take blocks and you reconfigure them and create new combinations of them built together, okay, to make a new substance. So, for example, one of the things that we can see is if I look at my one major type of reaction here, and this is called a decomposition. This is right here. Substance AB would be an example of a compound because we have two different elements within there. We have element A and we have element B attached together. So a chemical reaction, an example of how this could work, is if we take compound AB and split it apart into its individual atom components, A and B. These are the new products that we make. Okay, so that there is how chemistry works. It doesn't work by changing an atom's identity, doing something like alchemy. It works by taking what's already there and making alterations as needed, okay, to the combinations and how we build them. So just what are a few signs of a chemical reaction? So how can we spot one of these if we're not looking at an equation? Well, with our eyes, right, we can see things like a color change, okay? So if we go from clear to yellow, we can see things as gas being produced by a reaction, right? We've seen in our class so far that heat is a great sign of a chemical reaction, and light being produced, right? So if we put two things together and a bright light shines and comes to your eyes, then you can probably sense that there's probably a chemical reaction occurring there. Now, there's one more sign of a chemical reaction that we've talked about, and that's called a precipitate. Now, a precipitate is a special kind of solid that forms when two what we call aqueous solutions are added together. So aqueous, you might hear the word aqua or agua, okay? That just is a water-based solution, okay? So something that's dissolved in water, when you add two liquidy, clear-looking solutions together and a solid forms, that's what we call a precipitate. So in this test tube over here, we can see a chalky kind of white precipitate form from adding these two liquids together. So here's a little pipette up there adding another solution into this here. And that's another sign of a chemical reaction, and we're going to talk about which kind of reaction forms these insoluble precipitates. So what's a little bit interesting about these precipitates is no matter how long you stir it or try to dissolve it, it will never fully dissolve into the liquid. Okay, so here are the different types of reactions we have in our class. The major classes we have are synthesis, decomposition, organic combustion, single replacement, and double replacement. So just as there is about 5 signs of a chemical reaction, there's 5 major types of reactions that we're going to talk about in this class, and a few special kinds of decomposition. So let's get into and let's look at the synthesis reaction. So a synthesis reaction is basically when you take 2 or more elements, combine them together, and form one compound. Okay, so the way you can think of this pattern here is you can think of it as A plus B goes to AB, or in other words, some students like to think of it as element 1 plus element 2 goes and makes a compound. Okay, so what you should see here is you should see 2 reactants, and I should actually say here, or more, going to be made into one product, which is usually a compound. Okay, so in this example, we have 2 distinct elements of chlorine gas, and we have cesium, which is a solid, so that's why it has an S next to it. Chlorine gas is a gas because it has a G next to it. Okay, those are called our states of matter. And what we do is recreate cesium chloride, which is a compound of those 2 elements. All right, so that cesium chloride to the right, that product of the reaction, is a new substance, but we didn't create anything new per se, right? We just added two different atoms together to make our new substance. Okay, so that's the distinction here. Not creating new atoms, we're just rearranging what we have. Okay, so synthesis, put two things together. You should see two reactants or more to the left of the arrow, making one product to the right. That's our clue, and that's our big pattern here to find that one out. Now, a decomposition is just the opposite of a synthesis. So what you have with the decomposition is instead of going from element to compound, we're going to take a compound, or you can think of it as AB, and split it into its element components. So here, we can think of it as compound going to element 1 plus element 2, or AB going to A plus B. So that's like the breakup reaction. Okay, so synthesis is like getting together. Sometimes we got to break up too. Okay, so this is a breakup here. So, for example, what I have is in this reaction only, the big tip, I want you to star or asterisk this. You're always going to go from one reactant in this class to two or more products, okay? So if you see one thing to the left of the arrow, chances are it's a decomposition of some kind, okay? So that's a big pattern, a little hint here. So you can see that there was a break between the potassium and the chlorine here, and what we have is we have those two elements on their own now, okay? Often this is done through the addition of heat, so you'll sometimes see a triangle written above these arrows to signify that heat was used to break these particles apart. Okay, now there's two different types of decompositions that are special in this class, and these are the ones that students tend to have a lot more trouble identifying. We have the decomposition of a chlorate, and we have a decomposition of a carbonate. I'm going to start with the chlorate first, as it is a little bit of a cleaner decomposition. Okay, so why this is called a decomp of a chlorate is because we're going to take any metal plus the anion of chlorate, and the anion of chlorate here is ClO3. Okay, you have to see that exactly. That's on the back of your ion sheet on the periodic table. And what we're going to do is we're going to take that metal in chlorate and split it apart into something that we call a metal chloride. So a metal chloride is basically an ionic salt. It's any metal plus chlorine attached to it to make a balanced ionic formula. And then we're also going to create oxygen gas. So where this break occurs, and it's easier for students to spot this one, that's why I start with this, is it really occurs between the chlorine and the oxygen here. So imagine we take this compound, we heat it up or something, and we're splitting the oxygen component of the compound away from the metal and the chlorine part. Okay, so this is kind of where the split occurs. And as that split occurs, okay, what we create is we create that lithium chloride and that oxygen. Okay, so this can be done with any metal plus chlorate. So for instance, we can have something like sodium chlorate. So it's also an alkali metal. We can start it in the solid form, and we can turn it into two NaCl's once that is balanced, and those three oxygens as well, okay? So that's how the chlorate decomposition works. So what you're really looking for is any sort of metal attached to a chlorate, and it should only have one thing to the left of the arrow. Now, that's the decomposition of a chlorate. That's a little bit cleaner of a breakup than what we're gonna see on the next one. The decomposition of a carbonate, same idea, any metal plus carbonate. What it's going to do, though, is going to split into a metal oxide and carbon dioxide. Okay, so when I look at this reaction pattern, again, you should see only one thing to the left of the arrow, so one reactant, but we're going to be splitting it in a little bit of a weirder spot. So when I look at this split kind of happens between the metal and the carbonate anion. So that carbonate anion is the CO3 guy that we're seeing right here. And within that CO3, okay, you can notice that there's kind of two parts of it that you can almost see. You can see that we can split CO3 into one oxygen that attaches to the metal here and CO2. So CO3 contains three oxygens. What's really happening is one of the oxygens are attaching to the metal, and the other two go with the carbon to form that carbon dioxide gas. Okay? So again, this could be any metal plus carbonate splitting into a metal oxide and the CO2. Just be really careful. Some students misidentify this as a decomp of a chlorate. because they don't see the L there next to the C. And a chlorate contains a chlorine and an oxygen. A carbonate only contains carbon and oxygen. All right, so next one is organic combustion. This is the burning reaction of chemistry. So when we're doing a combustion, that is the exciting one that you all like. It's when we burn something, okay? So this is where we take something called a hydrocarbon. A hydrocarbon is a compound containing carbon and hydrogen in any amount. And what we do is we add it to oxygen, which is just the chemistry language of burn, and we create two products every time. So the way to spot this reaction is you will always make water and CO2 every single time. Okay, so whenever you're looking for an organic combustion, look for those two products. All right, so there you go. Now, what we call this as well is we call this a CHO reaction, and I like to say that because these reactions, another hint to find this, only contain carbon, hydrogen, and oxygen. So if you're ever looking for this reaction, look for carbon, hydrogen, and oxygen only being present in the reaction. Okay, so that's organic combustion. Those are always you guys' favorites to balance. So look for those difficult equations to balance, and it's probably an organic combustion. All right, so last two reaction types that we have are single replacement and double replacement. So the single replacement, I like to call it the date-stolen reaction. Okay, and here's why. When you have a single replacement, this is probably one of the harder ones to spot. You're going to start with a compound of any type, and you're going to start with an element on its own. Okay, and what's going to happen is if you look at my picture of these circles, do you notice what has happened to the yellow circle? Well, what you should see with the yellow circle is you should see the yellow circle has kind of taken the place of the blue circle with the pink guy in the compound. Okay, so what happens is we essentially take one element here. The element kicks out one of the other elements in the compound, and we form a new element in a new compound. Okay, so how does it look in chemical equation form? In chemical equation form, let's say we start with this potassium here. So there's my potassium, and here is my metal magnesium. So these single replacement reactions, either a metal replaces a metal or a non-metal replaces another non-metal. Okay, so what we can see that has happened here is we take potassium in its solid form, and that potassium is more reactive than the magnesium. So think of it like, I don't know, everyone's like 6'5", finance, whatever, takes over this magnesium cation here. And what's going to happen is the K kicks out magnesium. So think of K as like the better date. The better option comes around for chlorine, and the better option kicks you out. And now you're out on your own, poor magnesium. Okay, so there we have the metal kicking out the metal. In this one, below, we have fluorine on its own initially as a gas and NaCl. Now what's going to happen here is instead of a metal replacing a metal, you might notice that the chlorine ends up on its own to the right as a product, and the fluorine is now part of the compound in the product side. So in this case, the F kicks out the Cl. Okay, so that's a non-metal replacing a non-metal. So it's only one replacement, so that's why we call it a single replacement. And there we go. That is our reaction type. So one metal replaces the other in a compound, stealing the date. All right, double replacement's a little bit different. This one is a double swap. So this only occurs with the metals. And so we have two metals here, the K and the Ba, and to the right, we can see that the Ba has almost switched spots with the K. Okay, so we have a double swap here where both metals are going to start with one anion and then they're going to end on a different one. Okay, so they both switch spots. The K starts on the SO4 and the ends on the NO3. The Ba started on the nitrate and ended on the SO4. Okay, so the way to spot this is a little bit of a hint is you're going to have 4 different compounds in your equation. Okay, so you're going to start with 2 compounds and then you're going to end with 2 different compounds. And that's what we call a double replacement. So you should see all compounds there. So think of it as like a double swap. I don't know if you've ever done like a swing dancing or line dancing, square dancing, like you double switch partners. This is kind of what it's like. But this one, it only happens between metals. All right, so rule of thumb on this one, if your equation's really, really long, chances are it's probably a double replacement. Now, in my description, I say that you often form a precipitate. So you'll see that both sides of both compounds in the left side of the equation are in the aqueous form, and one of the compounds often ends up being solid to the right as a product. So this BaSO4 would be our example of a precipitate. Okay, so those are your different patterns. It's a lot of information, and to be honest, it just takes a lot of practice to start identifying these more effectively. Okay, so what I did in class, if you weren't here, is I went through 5 different reactions in person, and I classified them, and I looked at the patterns. Okay, but what I'm going to do is I'm going to kind of demonstrate how I go through 2 skills. 1, identifying the type of reaction, and 2, predicting the products of a reaction, which is where we're going to be going soon in this class. For first exposure purposes, I don't have you guys do this, but I show you what I'm doing, and then eventually we'll get practice and predict what products go to the right of these arrows here. Okay, but for now, we're going to focus on the classifying portion. Okay, so how do I use that chart and how do I classify reaction? First reaction, I see that I have iron and oxygen to the left of the arrow. So what I'm spotting here is I'm spotting element 1 and element 2 being added together. So when I go up to my chart on the first page, I'm looking for a pattern where I'm adding 2 elements together. Well, in the pattern here, if I check it out really closely, I can see that the synthesis reaction shows that in one element and another element coming together to form a compound is the pattern. So this is probably matching that pattern. What I'm going to do here is I'm going to go ahead and I am going to add these 2 elements together and make a single compound. In this case, I'm going to go and make iron oxide. Now, we know that iron comes in a few different forms. Iron comes in the +2 form and the +3 form. I would tell you in the problem which one to use on the right side of the equation. In this case, let's go ahead and use the +3 form to make this balance a little bit more interesting. So if this is iron 3, oxygen has a 2- charge, and so that means I'm going to need 2 iron 3s and 3 oxygens to balance this out. Okay, so we're going to start doing our balance equation. At this point, we always start with iron, so I'm going to go 2 in front of the iron there. And then after that is done, we are going to balance the oxygens. Well, here I have a 2 and I have a 3, so I need to find their least common denominator, which is going to be 6. All right, we see here that that's not going to work. So to get this to 6, I'm going to add a 2 in front of the iron. Okay, now that fixes that oxygen situation, so I can put a 3 here. And just to make a final adjustment to that iron, I'm going to add a 4 in front. Okay, so synthesis reaction. By knowing it was a synthesis, I was able to say that I'm going to make one compound and predict that product. All right, let's go to the next one. This one, we have copper carbonate, okay? And this here, I don't actually have to tell you the charge of the copper. You can tell by the fact that it's paired up with the carbonate. So this is going to be copper 2 carbonate to make that a neutral ionic compound. I see one thing to the left of the arrow, which means I have one reactant. Let's check our chart and see what pattern this matches. Okay, so we probably see that there's one reactant, so that's probably narrowing in on our decomposition here, because that's the only reaction type where we can have 1 to 2 or more things being made. Now, which decomposition is it? Well, I just said it's copper carbonate being decomposed, so this is matching our decomposition of a carbonate reaction. So what I'm going to go ahead and do is I'm going to go split this up following that pattern. In that pattern, it says that we're going to take the carbonate and split it into a metal oxide and CO2. So that means, as we remember, right, that the split is going to usually happen between the metal and the carbon dioxide, and one of those oxygens is going to head on over to the copper. So if it's copper 2, that's a 2+ charge, it's going to pair up with 1 oxygen. Then we're going to add whatever gas we create. So if we took 1 oxygen away from CO3, that means that we're ending with a CO2. All right? So this was our decomp of a carbonate. All right, so first things first, look at the pattern. Second thing, go ahead and predict those products. All right, so moving on to the next one. Since that one's already balanced, we already have the proper number of coppers, oxygens, and carbons, so we're good to go. All right, what we're going to do is we're going to take a look at this third one now. I'd like you to go up to the chart and try to figure out what pattern this third one matches. Okay, so hopefully you've given it a try. Let's go ahead and narrow down a few of the options that we have here. So this one, we have a CH3OH plus O2. I see two things to the left of the product side. So that means by default, it cannot be any of our decompositions. All right, synthesis, is it two different elements being added together? Well, in this one, no, right? We have a compound plus an element, okay? Well, is it single or double replacement? Double replacement will require 4 different compounds. Single replacement has 1 element plus 1 compound. However, we should see things like metals in the formulas, which we do not see here. So this is a CHO only reaction, which means it's our organic combustion, okay? And the nice thing about an organic combustion is once you know that, the two products are always the same each time. The two products of an organic combustion are always going to be water and CO2. So we know every time when we have an organic combustion, we're going to be adding those two things together. Now, if we were really good here and I was writing on all my states of matter, I would say we're probably going to make gaseous water and gaseous carbon dioxide, putting 2 G's there if we get this reaction hot enough. Okay, so now that we have this going, let's go ahead and balance the equation. Now this one, I'm going to warn you right away, it is a little bit trickier. Okay, so if we start with the carbon, we have 1 carbon and 1 carbon, so we're good to go. If we go to the hydrogen, we have a 3 plus 1, so 4. So that means that we have to put a 2 to the right of the arrow there. Okay, once we do that, now we can look at the oxygen. We have a 2 times 1 plus 2, which means we have 4 to the right. However, we have a 1 plus 2, which is 3 to the left. And that's going to be a little bit tricky for us to balance, and chances are this is not going to work out right for us. So what I always tell students to do is take the whole equation and multiply every coefficient you have written down by 2 and try to balance again. So that means that 2 is going to go here, which would then lead us to put a 4 here. Once that 4 is there on the H2O, now we can worry about the carbon dioxide and we can worry about the H. So if this is a 2, then that means there's also a 2 there. Okay, let's look at the oxygen now. So we have 2 times 1, which is 2, plus another 2, which is 4 to the left. We have a 4 plus 2 times 2, which is 8. What that means is in front of the oxygen to the left side, to get that magic number of 8, we got to put a 3 there. Once we do that, now we have that magic number of 8 and everything's balanced. Okay, so if you're in class, you would have seen me do what I call the whoosh bottle demo, which is basically taking gaseous methanol, which is an alcohol, and igniting it inside a plastic bottle called the whoosh bottle, and a nice flame comes up. It's a pretty cool demo in person. Okay. One special thing about this is actually not a hydrocarbon to the left. This is an alcohol, which is the other thing that we can burn with oxygen in organic combustion. All right, the next one. So let's take a look at these guys. So for this one, what we have is we have an element and we have a compound. And what are they going to turn into? Well, let's find the pattern. What pattern up here involves an element being added to a compound? Okay. Well, we just did the organic combustion, but in order for it to be an organic combustion, it has to be CH&O only. Here we have metals reacting with each other. So the pattern that this matches with an element and a compound reacting is our single replacement, or SR for short. So if this is a single replacement, copper is going to come in, this one that's on its own, and kick out the metal in the compound. So this is going to make, in this case, copper 2 nitrate. So that means that we're going to need 2 nitrates here. And it's going to make, really importantly, solid silver. Okay, so that's why I put an S there. If we're being really good, I would have put an aqueous by that copper nitrate. And then once we're there, we got to go ahead and balance out the reaction. A 2's got to go in front of the silver nitrate because we have 2 nitrates here. And then a 2 goes in front of that solid silver. Okay, so how do we see this single replacement in class? This single replacement in class, what I did is I put a copper wire in some silver nitrate solution. So this solution comes in a brown bottle. It's clear. It has a slight silverish tint to it, if anything. And it's actually used in developing film in photos. And I added a copper wire to it. And over the course of the class period, what we saw that the silvery kind of solid was growing and crystallizing on the outside of the copper wire. Well, what that was is that was solid silver. And the solution surrounding the wire was actually turning blue. Well, copper 2 nitrate is an aqueous solution, has a bluish tint. And what we should be seeing is that was the solid silver being kicked out of the solution and turning into a solid forming on the outside of the copper wire. So over time, what we should see is a bunch of solid silver crystallizing there as the copper kicks the silver out of the aqueous solution. All right, last one that we have is we have one with 4 different compounds. The only pattern this matches when we have 4 distinct compounds is the double replacement. Okay, so when you think double replacement, think double compound. Okay, so I'm going to abbreviate that as a DR. Now, this here is already written out for us. Okay, again, I'm seeing a bunch of different compounds here. To balance this just requires a 2 to get 2 Ks and 2 Is. And so what I did in class is I added these 2 aqueous compounds. That's why there's AQs next to those compounds. And what we formed was a solid called lead iodide. Okay, so here was our potassium iodide that I added. I added it to a little test tube. In this case, it's a beaker in this picture. And the potassium iodide solution in the lead nitrate, the lead in the potassium switch, and this yellow solid chunky substance formed in the test tube. And that chunky yellow substance was our lead iodide. All right, and so that is what we again call our precipitate. All right, so that's the general skill of what we're looking for you to be able to do. This table is going to be a really helpful thing for you to use going forward in this class. And this just takes a lot of practice, guys. So the more practice, the merrier. So go down here to the chemistry section and try these out on your own. This is what we're going to do. You're going to look at each equation. You'll balance them and put the coefficients in the blanks here to balance the equation. And then you'll classify each reaction type. Okay, so is it a single, double, organic combustion, decomp, or synthesis? Good luck.